Hey guys, so welcome to my talk. So today I'm going to be presenting work on enabling additional parallelism in asynchronous JavaScript applications. So this is work I did with my advisor, Frank Tipp at Northeastern, and then our colleague, Max Schaefer, who works at GitHub. So if you ever see us in person, if there's real life conferences again, it's basically what we look like. So feel free to say hi. Okay, so let's get into this. I'm just going to quickly give an outline of my talk. So first I'll present the problem and then the solution that we're trying to reach. Then I'll present the approach that we're using to try to get from this problem to our proposed solution. And then at the end, I'll just talk a bit about our evaluation of this work. So basically, JavaScript has this async await construct that got added with ECMAScript 6, I believe, in 2015. So what is async await? So the async keyword is just a label that you stick at the front of a function definition that says that any invocation of this function is allowed to execute asynchronously from the main event loop. So really, that's a fancy way of saying that it can run concurrently with other parts of the JavaScript code, depending on whether or not these other things that are executing can dispatch things to outside of JavaScript runtime. So in this example, we see there's two await statements. Now, await is kind of analogous to a thread.join, but the idea is essentially that it's just a tag that says we're going to wait before we continue with the execution of this code block for the computation that's being awaited to finish executing. So in this case, we see a call to read file. So before we do n++, we're going to read foo.txt. And then before we do n++ again, we're going to read bar.txt. So that's it. Now, the problem is that it's very easy to just put awaits in front of everything that has an asynchronous computation and not really think about whether or not this is an optimal ordering of things, or like whether or not the awaits are really necessary in the particular format that people specify them in. So in this example, we see that there's two read files, and it turns out that this is independent file IO. There's no reason that the first read file has to finish before the second read file can start. So our proposed solution is to move the computations that are being awaited, so the promises, as early as possible in the program, and move the awaits themselves as late as possible in the program to allow for maximized basically opportunity for parallel executions to happen. So here's kind of the same example that we just saw, but rewritten with our proposed solution. So you'll see that the read files got moved to the top of the function, and then the awaits got moved lower down. So they're adjacent now to each other. And this allows the asynchronous and parallel file IO that's being called in the background just through the operating system to run in parallel. So now, of course, as you may have guessed, it's not as simple as saying, all right, take all the promises and move them as early as possible, take all the awaits, move them as late as possible. We need to figure out how we know what we can move. So there's kind of a few things that are involved here. We have to keep track of the variables that are accessed and modified. So you'll notice in our refactored program that we didn't move the awaits after the console.log. The reason for that, as you probably figured out, is because the print statement uses the value of the variable s, which is modified by the result of the asynchronous computation. So because these read files are basically modifying the s variable, we can't change the order that they're executed with respect to other things that are modifying the s variable. We also need to keep track of environment-specific side effects. So by environment, I mean the environment of a particular source of asynchronous IO. So this is the same example as before, but now I've added a write file. So here we see that now we're writing to file bar.txt before we're reading it. So if we were to change the order of execution of the read file and the write file, that would change the behavior of the program. So then it would be an invalid refactoring. So we need to track the fact that this write file is a modification of the file system environment. you'll notice that there's no shared variables that are being modified. It's just the contents of this file. And then JavaScript also has this wacky thing where you can just execute arbitrary code snippets in the middle of a program. So this eval function is one example, but it just takes in a string, and then whatever string gets passed in, it just turns into code and executes it. So we don't have a way of knowing what code is getting run if there is an eval statement found in a program. So then we have to conservatively assume with our analysis that this modifies all present variables and resources, so the environments as well. Just because if we were to try to actually figure out what was running, we would need to fully parse the entire code that is in the string. So now, how do we track these variables and environments and all that? So for this, we use the concept of mod and refsets. So the mod set is the set of all of the variables and environments that are being modified by a statement, and then ref is the same thing, but for just references. So think read versus write. So I'll go through some examples from this code so you can see what these sets look like. So for the highlighted statement, we see that the only variable being modified is s, because s is being incremented. So we see s plus equals. Now there's a few things that are being referenced here. So we see s is referenced here as well because the plus equals uses the previous value of s. fs.promises.read file. So everything in that chain of accesses is being accessed. And then finally, we see this all caps file system variable. And this is our representation of the file system environment. So it's just like basically a fake variable that we introduce, but just to make sure that we track what statements are using what environments. So next statement, pretty straightforward. The incrementing of n modifies n and also references n. Now the next read file has the exact same mod and ref sets. So you'll notice it doesn't matter what string, like what file name is passed into the read file, the mod and ref sets are the same. And then n++, again, mod and refs, both n. Big surprise there. So finally, we see the last statement is this print statement. So this doesn't modify anything, but it does reference s, n, and then everything involved with printing to console. So now we track what statements we're allowed to move and like the reordering that we're allowed to perform by way of comparing the mod and ref sets of the statements that we're thinking about swapping. So basically what we want to find are instances of when there's conflicts between these sets, because that indicates a data dependence. So in this example, we see, this is just the example where we added the write file again. So here we have the await statement where we're reading a file, and this references the file system. Now, when we're writing to a file, we're modifying the file system. Sorry for the thunder in the background there. But yeah, so anyway, the point is that because one statement is referencing something that the other statement is modifying, we know that the order of these two statements relative to each other must be preserved. So we can't swap them around without changing the behavior of the program. So to sum up, we built a static analysis. This is a side effect analysis. And first, we find await statements that are dependent on specific sources of asynchronous I/O. And then for each statement in the relevant scope, we find the mod and ref sets. And then these are made up of variables, environment-specific side effects, and global side effects. So two statements are independent if their mod sets are disjoint, and then the mod and ref sets of each of them are disjoint. So essentially, this just means the two statements are independent if neither of them is modifying something that the other one is modifying or referencing. So in terms of the implementation of this tool, we wrote this using the CodeQL language out of GitHub, and I'm not really going to discuss the implementation, but if you're curious, The source code for the tool and all of our data and our experiments are available at this link. This link's also in the paper, and we have an artifact as well. So, evaluation. So what did we evaluate? So, of course, we're trying to increase parallelism. It stands to reason that the intended effect is that we see a performance increase, right? So what we wanted to do was measure the effect on the performance in practice. So we used 20 open source JavaScript applications. So these are just projects from GitHub. 15 of these were dependent on file system IO, and 5 of them were dependent on network IO. And then for each of these, we measured the performance impact on the application's own test suites by way of experiments as follows. So we found the relevant tests, and here relevant means the tests that are executing the await statements that are candidates for refactoring. So we time each of these tests, then we do the refactoring, and then we time the test again. And we did each of these things 50 times for each project. So then, given all those results, we compare to see with a t-test if there's a statistically significant performance change, either positive, so a speed up, or negative if there was a slowdown. And we didn't see any slowdowns. So here's a big table that, of course, I'm not going to go through line by line. It's mostly just here in case you want to reference it in the paper after. But the takeaway is that overall, we saw an average 8.1% speed up on the applications tests for the projects where we performed refactorings. So I'll look a little bit more closely at one of the projects in particular. So the Cactus project, we see an average speed up of 7.8%, which is fairly close to average. And I've chosen it just because it has a large number of tests. So the results are a little bit more informative. So here we see that we're graphing all of the tests and then the percentage speed up after the reordering for each test. So the dark colored dots are ones where the performance change was statistically significant. And we see that in the majority of these cases, like in the majority of these tests, we do see a statistically significant performance increase, which is really cool. Yeah, and then the mean is just in red. So that's the 7 point whatever percent it was. Now, it's also interesting to look at specific runtimes. So remember, this graph gives you the percentage speed up after the reordering for all the tests. We can't directly compare the runtimes because the tests have different runtimes that are completely independent. But if we do look at the runtimes for each test, we notice something else that's interesting. So not only is the average runtime decreased, so we see performance win, but also, interestingly, we see that there's much less variability in the runtimes of the tests. So the clustering of the blue dots, which are the reordered code, is much closer than with the original code. So intuitively, that makes sense because once we've enabled more parallelism, if there's something that disrupts the computation, so for example, if your system just runs like a log file print, something that stops your computation, it'll have much less effect if you have more potential for parallel execution in the background. So in summary, this project was for reordering await statements to increase parallel IO execution in JavaScript programs. We used a static analysis to determine statement independence, modeled as mod and refsets. And then on our tested applications, we saw an average of 8.1% speed up. So at this point, future me will take your questions, and thanks for your time. And I've just included the link and our pictures again. So feel free to say hi in the future. That's all I've got.